Hi everyone, this is Wentao Yan from National University of Singapore. Today I'll talk about our work on multi-physics modeling of electron beam additive manufacturing from powder spreading to preheating and to melting. Today I'll divide my presentation into two parts. First is modeling of electron beam additive manufacturing process, including powder spreading, preheating and sintering, and powder melting. And second part we will extend to process structure property relationships. So actually we know electron beams additive manufacturing have three major procedures. The first procedure is powder spreading. So we build a model for powder spreading using the discrete element method, where we include elastic and inelastic collisions, frictions, and gravities. Moreover, we also incorporate the rig shape, spreading speed, and layer thickness, as well as the powder size distribution. The second procedure is preheating and powder sintering. In order to investigate the solid-state sintering, we develop a model using the phase field model, where we consider grain boundary diffusion, surface diffusion, volume diffusion. And for the third procedure of powder melting, we develop a model using the computational fluid dynamics method, where we consider the heat transfer, phase transformations, and fluid flow. So to fully reproduce the multi-layer, multi-track electron beam additive manufacturing process, we link these models together. So we use the powder spreading model to generate the powder bed geometry and implement into the powder melting model. And then after we finish the electron beam scanning, we got the solidified geometry and we implement back to the powder spreading model to spread another layer, and then we repeat this cycle. For the first procedure, powder spreading, the major objectives are first to generate elastic powder bed geometry for the powder melting model. Second is we want to understand and optimize the powder bed quality, including packing density and surface roughness. Third one is we want to use this model to at the design selection of the shape of powder rig or roller, spreading or rotating speeds, powder size distribution, and layer thickness. Actually, we simulate the rig type powder spreading as well as the roller type powder spreading. This figure are the experimental setup for roller type powder spreading. We have a portfoliometer to in situ measure the surface roughness of the powder bed. This is the experimental and simulation results. You can see with the increase of the spreading speed, the relative density is decreasing, and the surface roughness is increasing. That is, with the increase of spreading speed, the powder bed quality is getting worse. And for rig type powder spreading, we investigate the influence of powder size distribution and the layer thickness on the packing density. So we design this experimental design with different sets of powder size distributions and layer thicknesses. You can see the simulation and experiments agree well for different cases. With that, we can also find the optimal powder size for the given material and the given spreading conditions. But this is not widely applicable to different materials or to different settings. More importantly, we have deeper understanding on the underlying physics. So there are mainly three effects governing this powder spreading process. The first is so-called wall effect, or we can call it boundary effect. That is the substrate, rig, as well as force chain or force arc within the powder particles will become the boundary for the powder particle packing. So it will induce more porosity into the powder bed. Second effect is cohesion effect. due to van der Waals force for fine particles. And third one is percolation effect. So generally, people believe if we mix smaller and larger particles together, we can increase the packing density. But in reality, it's not like that, because in some situations, the smaller particles can be sieved by the large particles and then lead to segregations of small particles and large particles separately, and then the resultant packing density is not improved. For the second step is the preheating for powder sintering. So the objective for powder sintering include two aspects. One is we want the sintering to be strong enough to avoid powder smoke. But on the other hand, we want the sintering to be as weak as possible to ease the powder recycle and reuse. Then, how can we get the optimal sintering? So we need to understand the fundamental physics. So we have two experimental results to validate our model. The first case is done by Professor Feng Lin's group at Tsinghua University in China using their in-house equipment. So after we got the next sintered powder samples, we use fused ion beam to do the cross-sectioning and polishing, and then use SEM to observe the cross-sections of the sintered necks. The second case is actually from literature published by a group from UK. So after they collected their sintered powder, and they used X-ray CT to observe the sintered necks. And both experimental results show the ratio between neck diameter and powder diameter is around 0.3. Although the processing parameters are slightly different for the preheating, but the targeted preheating temperature is the same at 1003 K. What are the mechanisms for powder sintering? Is it liquid state sintering or solid state sintering? So we run a simulation to explore the possibility for liquid state sintering using actually the powder melting model, which we will introduce later. These are the results. You see the temperature profile at the representative powder particles. And for the first case, the peak temperature does not even approach to the liquid temperature. While for the second case, the peak temperature is very close to and a little higher than the liquid temperature, but the duration is very short. So in the simulation, there's no particle reshaping. That means the liquid state sintering should be minor. To investigate the solid state sintering, we develop a phase field model in collaboration with Professor Yongxing Shen's group at Shanghai Jiao Tong University in China. First, we investigate the sintering between two equal-sized particles at a constant temperature. Now we can see the neck size ratio reaches about 0.23 in 6 seconds, and is slowly approaching a stable state. And in experiments, the stable state is around 0.3. And we can see this can be a good agreement. And then we investigate the influence of preheating temperature on sintering. With higher preheating temperature, the sintering rate will be faster. But in experiments, below the preheating temperature of 873 K, there is seldomly sintering, and above 1003 K, there are always sintering. So we believe there is a critical temperature for the sintering between these two values. But in our simulation, we haven't precisely captured this. You can see in the simulation, the critical temperature seems to be between 600 K and 900 K. This inaccuracy is mainly due to the uncertainties of the diffusion coefficients of the material at high temperatures. Then we also investigate the influence of particle diameter on the sintering, and with a smaller diameter, the sintering net growth ratio is increasing more rapidly. So that means we need to consider using different preheating temperature for different sized particles. And also we investigate the sintering between two unequal sized particles. And naturally the net growth rate is between those of the equal sized smaller and large particles. Finally, we want to investigate the grain structures within the particles, how it influences the sintering. But the simulation results shows the grain boundaries within the particles do not significantly change the sintering behavior. So this is all we have now, but there are a few things can be added. For example, now we haven't considered the influence of oxide film on the sintering behavior. So for the third step, powder melting, this is the most extensively investigated topic, but our approach is a multi-scale approach because we want to make it more physically accurate. So we start from microscale model to simulate the interactions between electrons and atoms to get the Higgs model, and then in powder scale model we investigate the evolution process of powder particles, and in the microscale model we investigate the temperature field in the whole part. So from the bottom approach, we understand the mechanisms and predict outcomes. When we face design inverse problems, we can use a top-down approach. For example, if we want to fabricate functional gradient materials, we need to we can design the composition gradients in the large scale model, and then use a mesoscale model to select the powder and the fabrication parameters. And lastly, we can use a microscale model to optimize the experimental setup, like the acceleration voltage for the electron beam. So specifically for the microscale model, so actually we investigate the collisions between the high energy free electrons with the atoms in the materials, and also record their energy transfer. So we use Monte Carlo method to simulate millions of electrons impinging into the materials, track their trajectories trajectories of each electrons, and their collisions and energy transfer in the material, and also we track the backscattered electrons and the energy they bring away, which is the energy loss in the large scale. With that, we can derive a physically informed Higgs model. So there are four terms in this equation. The first term is the energy distribution in the cross-section of the electron beam. The second term is the energy distribution along the penetration distance. And the third term is the energy absorptivity based on the calculation of the energy loss due to the backscattered electrons. And Q final term is the setup power in the machine. And the governing equation for the collisions and energy transfer is actually from quantum mechanics. And is it accurate from, we model from quantum mechanics to a large scale? So a group from Canada, they use the same model and they also did some experiments to validate the model. And you can see at a different incident angle, the energy absorptivity agree pretty well between the simulation and the experiments. So that's demonstrates the accuracy of this model. The next question will be how to implement the heat source model from micro scale to the meso scale. So here's what we did. So first we reconstruct the free surfaces of molten pool and powder particles in the powder scale model using the volume of fluid method, like this, and then we apply a heat source model by dividing the electron beams into a number of sub-beams with varied energy. So the energy for each sub-beam is dependent in its location within the cross-section of the electron beam. Then, for each sub-beam, we find the free surface and then start penetration from the surface. And for the energy absorptivity of each sub-beam, it will be different because the local incident angle for each sub-beam is different. Then we'll apply the absorbed energy along the penetration depths based on the simulation results from the microscale model. In addition, we also apply recoil pressure, which is temperature dependent. For example, if the local temperature is around the boiling temperature, then there will be recoil pressure. And if the temperature is relatively low, there will be no recoil pressure. Lastly, we update the free surface at the end of each time step. To ensure the accuracy of this model, we make the mass size is to be around 5 micrometer and the time step size to be 50 nanoseconds. So this is one verification case to verify our model. So first we assume the energy is evenly distributed in the cross-section of the electron beam and impinged into a spherical powder particle. And you can see the similar results. The center of the powder particle gets melted first, and then the edges. This is because the incident angle in the center is 0, so the energy absorptivity is the highest. And to the edges, the incident angle becomes larger and larger, and the energy absorptivity becomes smaller and smaller. So that's why it gets melted later. And also you can see the subsurface area gets melted first, and then the surface. This is because of penetration. For the commonly seen Gaussian distributed electron beam, if the power is high enough, then there will be recoil pressure and the keyhole will be formed. We use this powder scale model to investigate the boiling effects and non-uniform track that are observed in the experiments, and we can better understand the underlying physics. So for the boiling effect, it's mainly due to the lack of remelting of the substrate, and then surface tension will drive the boiling. And for the non-uniform track, so when the molten pool is long, the fluctuation of surface tension will induce flow instability, and then there will be the non-uniform track. And to investigate the lack of fusion voids, we run multi-layer, multi-track simulation case. So this is, for example, this is a scan pass in one layer, and the next layer the scan pass may rotate for a certain angle. And so this is a case where the rotation angle is 90 degrees. We already run the first case, the first layer, and now it's the second layer, and this is just show the free surface. So this part will be the voids, interlayer, intertrack voids. So the shape, geometry, size, and space distribution of the lack of fusion voids in our simulation also agree with the experimental observations. So next we want to extend our process models to structure and property relationships. So the overall framework is like this. So link the process structure property models together. So when we get fabrication parameters, we input into the powder spreading and the melting models to predict the temperature profile and voice formation. And then we implement the temperature profile and voice into a grain growth model to simulate the grain evolution. With that, we can get the structure information including voice and grains, and this can implement into the crystal plasticity model to predict the mechanical properties. And with this, we seamlessly link this model together to replace most of the physical experiments, and we can shorten the R&D period. So specifically for the grain evolution model, so we consider the grain nucleation and growth. You can see this is a simulation for multi-layer multi-track, and this is a grain growth simulation, and this is a 3D view of the nucleation set at different tracks, and this is a cross-section view of the grain growth, and you can see the column, the growth of column grain, and also the remelting of the previous solidified grains. We compare this model against experiments, and they agree relatively well. Actually, within the dendrite growth, so it's within the grain growth is actually dendrite growth. So also we developed a model to investigate the dendrite growth. First, we compare the model against the theoretical LGK model, and you can see they agree pretty well. And also, we can simulate the growth of dendrites with arbitrary orientations. Furthermore, we validated our simulation with X-ray imaging results for directionally solidification case. And you can see the dendrite growth rate agree very well with our simulation results. Besides the solidification, in electron beam, the solid state phase transformation is also significant because the solidified materials will be maintained at an elevated temperature for quite a long time. So especially the precipitation process is significant. So we develop a precipitation model, and this is a comparison between simulation and experiments. And you can see the precipitation usually occurs near the grain boundaries. So this is also a good agreement. For the details for this model, I would strongly suggest you to refer to my student's talk, Yu Yefeng talk here. And finally, with the grain structure evolution from either grain growth model or experimental measurement, we can reconstruct the microstructure and then use crystal plasticity model to simulate the mechanical properties, and where we use mechanical tests to validate this model. And here are some brief results, including both tension and compression tests. It should be noted that the yield strength for tension and compression, there is a remarkable difference of around 400 megapascal. This is mainly due to the reduced stress. That means we need to carefully consider the influence of reduced stress when we investigate the mechanical behavior of additively manufactured parts. So overall, I just briefly overview our work on the modeling part of electron beam additive manufacturing. So if you want to know more details about this work, I would suggest you to read out related papers listed here. Thanks for your listening, and if you have any questions, you are very welcome to send me an email or in other ways we can discuss.